All right, so our last talk for this session will be DoS protection using multi-prefix query counting. And with apologies to our speaker, because I'm not sure I'm going to get this right, but I'll give it a try. Lukáš Ondráček from CZ.NIC.
Hello, I'm Lukáš Ondráček. I'm working at CZ.NIC on the knot resolver, and I will talk about our protection against the denial of service attacks. So we focus on two types of attacks. The first one is the amplification attack, when we receive many UDP queries with forged source address, and so we send larger replis to someone else. To mitigate this, we limit the rate of the responses. So when it's over the limit, we either drop the responses or send them as truncated. The other type of attack is when we again receive many requests from some host, and we don't have enough CPU time to process all of them. So we have to drop some of the requests. In this case, we measure time we spend on queries from the same host, and then when we receive another request, we assign it some priority level. So we reorder the waiting queries, and when there is not enough time to process all of them, we will probably drop the ones which has low priority. We use the rate limiting for UDP only, and we use the prioritization only for all other traffic, because it can even worse the issue if there are some forged IP addresses. And both of them are used for different prefix lengths, so we can rate limit individual hosts as well as larger networks. I will first say how to limit the individual hosts, then extend it to networks. After that, I will speak about the prioritization, and finally, I will say something about our internal implementation. So let's imagine we have a table with all IP addresses, and there is a counter for each IP address. I will say in the implementation part how to store only the relevant rows of the table. Now, when a packet arrives, we increment the respective counter in the table unless it would exceed its limit, in which case we send, or not send, we restrict the answer in that case. This way, we define the instant limit, which tells us how many queries are allowed from a new host in some short period of time, let's say. And we need to somehow decrease the counter. We will multiply them by a constant less than 1 each millisecond, and the constant defines us another limit which we call a rate limit. It's number of queries per unit of time which are allowed from a single host. I will show how these two limits works on this chart. So on the vertical axis, we have the value of the counter. On the horizontal axis, we have time. And the red line is the instant limit. Now, let's say we have received many queries from the same host, and so he hit the limit, and now he will stop sending the queries, so we can see the decrease of the counter. It will look like this: is the staircase-like line, and the height of the first stair is the rate limit. The ratio between the rate and instant limit gives us half-life, which is the time in which the value of the counter is halved. So it may look this way. It may be confusing how to set the two limits. So a simple advice is to set the instant limit according to what is considered to be the normal behavior of the clients. So how many queries we expect he will send in some short period of time. And we set the rate limit according to our performance of our server. It then gives us the half-life, which tells us how often we can handle the normal behavior of the clients. Well, there are other alternatives to exponential decrease. For example, the linear one. We have chosen this because it prefers the regularly sent queries to bulks of queries. So we consider this better. Now let's see how it looks when someone sends us queries regularly with some constant query rate. When the query rate is under the rate limit, the value of the counter may rise a little, but it will converge to some value which is under the red line. So it's not restricted. When we have the query rate which is above the rate limit, it will eventually get restricted, and as we count only the unrestricted queries, it will each millisecond drop by the rate limit and allow some queries to be answered. And if it's above the instant limit, even during the first millisecond, that is limited instantly. So this is how limiting the individual hosts work. Now let's extend it to limiting networks. We have chosen several important prefixes and assign multiplier of limit to each of them. So now we have in our table the individual hosts as well as the networks, and the networks have the limit multiplied by the constants. Now when we receive a packet, we try to increment all of the relevant rows unless any of them overflows. So in which case we again restrict the answer. So if any overflows, we do not increment the address, which is important because we don't want to count these queries in larger network and possibly perform some restrictions there, and we don't want to send to count it in individual hosts because we don't need that information, and it would be wasting of memory. The other advantage is that for the restricted answers, we need only read-only access to the table, which is faster. And what I haven't said, how to distinguish whether we want to send the truncated answer or the answer at all. For this, we use the standard slip mechanism, which was implemented elsewhere. So we send some constant fraction of the queries as truncated. We need to send some queries as truncated because if the victim sends also some queries to us, we cannot distinguish them. And if he receives the truncated answer with some constant probability, he can reconnect using TCP and get his answer there where the limiting is not performed. So this is how rate limiting works. Now let's move on to the prioritization. This is the process of resolving a little simplified. So the important thing here is that we receive some packet with a query, then we process it for some time, we send query somewhere else, wait for the reply, and so these two phases are switching, the processing and waiting. And during the waiting phase, we can process another queries. So we measure only the time of the processing, and we increment those times to our table. This is another instance of the table. So we have one instance of the table for the rate limiting and the other for the prioritization. And here, the values in the table represent the times in microseconds. Now, when another packet arrives, we look in the table, and according to the values, we assign it some priority level. And according to the priority level, we push it in one of several queues, or we process it immediately if the priority level is high enough. Then when we have time for processing other packets, we process the queues according to the priority levels. And when we find some packet which is too long in its queue, we drop it. So this is how the prioritization works, and now how the table is implemented. We start with a simple hash table where we compute hash of the address, and we use part of the hash as index in the table. And we will gradually improve this solution. So the first improvement is that we use buckets in the hash table, and each bucket can contain several rows with colliding hash. To lower number of collisions, we will use in fact two hash tables hashed independently, and the row can be found in any of the two buckets which we find according to the hash. Now let's imagine it's not there. In that case, we need to evict some record there. So we start with normalizing the values to the same limit. Let's say to the limit to 16. And we also rescale the increments for this. Now when the value is higher, it is closer to restriction, so it is more important. So we find the lowest value and we want to evict it. But we will not evict the whole line, we will just change the label. This way, when it happens that multiple addresses will keep evicting each other, they will in fact share their counter instead of get 0 all the time. This resembles, for example, count-min sketches, which are used for getting some statistical information about streams in sublinear memory. So it's beneficial to use it this way. Now another thing we want is to perform the decay of the value. So we want to multiply each value by the constant each millisecond. We will not do it each millisecond. Instead, we store a timestamp in each bucket, and every time we access the bucket, we will perform the decay on all values values there according to the difference of current time and the timestamp, and we will update the timestamp. So now, how to store it in memory in more condensed way. Storing the addresses there are too long for storing. So instead, we store another part of the hash as the label there. There is only a few rows in the two buckets, so the number of collisions, the probability of collisions is very small here. And now what to do with the values? Internally, we perform all calculations with the values in 32-bit arithmetics, 16 bits of the whole part and 16 bits of the fractional part. And before storing it, we round it. But we perform the rounding probabilistically. So we take the fractional part as the probability to round the number up. This way, we can perform increments of even much lower values than 1, and still very reliably recognize when we hit the limit. So our stored values are also 16 bits, and we store 15 rows in a bucket, which means that the whole bucket will be 64 bytes long, which is the same as the cache line. So each time we access the memory, we need to transfer the whole cache line. So let's use all the data which are stored there. Now we need only 2 memory accesses for one query on a specific prefix in the table, and for the whole queries and at most 5 prefixes, we need at most 10 queries. To speed it up even more, we use prefetching. So we first say how many. We first determine which cache lines we will need, and then access them. we use atomic instructions, so the data structure is totally log-free, and we use vectorized instruction from the AVX and SSC extensions of x86 instruction set to search for values in the buckets to speed it up even more. So this is it. If you want more details on this, you can read our blog spot on the conceptual part, which was the first part of the presentation, or soon another blog post about the implementation. So thank you for your attention.
Hi, John Todd from Quad 9. Question about how you implement this, going all the way into actually the configuration. The back end is very interesting, but it sounds like you're dropping queries basically just based on IP address. When you get a certain level, or looking at the drop method, you're looking at just number of queries that don't match or that are above a certain limit. Is that correct?
Sorry, once more, please.
Are you dropping queries simply based on IP address at this point?
Yes.
Okay. Is there any thought to extending that further into the protocol stack? To give you an example, looking at a client that's sending you too many PTR queries and then executing your method only on the matching queries that fit a certain criteria instead of all of the queries from a certain IP address. That adds an additional couple dimensions to your method. So does the method only work on just IP addresses, or does it work deeper into, or is it applicable deeper into the protocol itself?
Currently, it's only by the IP addresses. We want to extend it according to like what domains are queries, to limit the rate of queries for some domain or something like that. But it is not yet implemented.
Okay.
We will think about it.
But you see that that's possible. That's something you're thinking about. Okay.
Yes.
Thank you.
Thank you.
See, if I understand correctly, you are not using the actual value but a hash. So I think that you can use whatever input you want because you hash it, and in the end, it's just bits. I think, is that correct?
Yes.
Yeah. And one thing I'm not clear about is how do you handle, for example, the attack when someone is spoofing the source IP addresses in a way that it's basically all of the IPv6 address space. So basically you see all the addresses. So what's the limit which prevents you from consuming all the memory you have by like filling the memory with the tables?
Well, the table occupies constant memory. So it only happens that the IP addresses will evict each other in that case. And well, if it's spread over the whole range, we cannot determine whether it's regular traffic or not. So
Sure. Okay, I will probably need to catch you with pen and paper. And thank you.
Thank you.